Click the bell icon to get latest videos from Ekeeda.
Hello friends, I welcome you all. Here we are going to solve a problem based on to the single stub matching. Here we are with the unit of microwave engineering for the transmission lines. So microwave transmission lines we are analyzing. So we started with the help of the circuit model involving the lumped elements RLGC. We have also derived the transmission line equations for the voltage form and the current form. Now we have the knowledge of reflection coefficient, transmission coefficient, what exactly the standing wave mean. The standing wave ratio is also formulated. We have the knowledge of line impedance and line admittance also, and all this information related to the analysis of transmission line we have used with the help of the very popular graphical method that is called as Smith chart. So based on to the Smith chart, we have also solved the two numericals associated to solve the problems for the transmission line. So as in the previous video, we have discussed a method of single stub matching so that the characteristic impedance should be exactly matched to that of the load impedance, so that the transmission line should be a flat line with no reflections. So let us have a practice of one problem. So here we are provided with a problem statement. The problem statement is a lossless line of characteristic impedance R0 is equal to 50 ohms is to be matched to a load ZL is equal to 50 divided by 2 plus J in the bracket 2 plus under root 3 ohms. So this is by means of lossless short circuit stub. The characteristic impedance of the stub is 100 ohms here. We are asked to find the stub position that is closest to that of the load and length so that a match is to be obtained here. Now to look at the problem statement, we come to know that here for the given the transmission line which is of lossless type. So a lossless transmission line is under consideration. We have a lossless type of the short circuited stub. So this is the single stub we are using for the purpose of matching. So hence the problem for single stub matching here. Now we have the two lines we can say here, the original main line and the short circuited stub line. So for the main transmission line, we have the characteristic impedance that is R0 is equal to 50 ohm, whereas for the stub the characteristic impedance is of 100 ohm. So we have the different values of characteristic impedances for the transmission line and for the stub. For line it is 50 ohm, for the stub it is 100 ohm. Now for the transmission line we have the load impedance given by 50 divided by 2 plus j times 2 plus under root 3 in terms of ohm. So here the division is to be taken place and we have the complex representation. So the real part and that of the imaginary part will be there. So for the load impedance we have the pure resistance represented by the real part that we may compute, and the pure reactance form will be associated with the J factor here. So now this is the generalized load impedance. We have to make it in the normalized form and then we can put it onto the Smith chart so that the further processing we can carry forward here. Now what is asked in this particular problem statement? Now we have to find the stub position, and the stub position should be closest to that of the load here, and the length of the stub also we need to determine so that the match is to be obtained here. So let us make the use of the Smith chart, and by the step-by-step process we shall be finding the stub position and the corresponding length, so that there it will be the transmission line made as flattened line here with no reflection, because it will be matched to the corresponding characteristic impedance here. So now the normalized load admittance can be represented as small y suffix l, and it is obtained as the inverse of normalized load impedance small z suffix l. So it can be the ratio of capital R suffix 0 divided by capital Z suffix L. Now these values are with us as per the problem statement. So by the next step, the normalized load admittance can be, we have 2 plus j in the bracket 2 plus under root 3 here, because R0 is holding the value 50, and if you get back to the problem statement, we have ZL value 50 divided by 2 plus j times 2 plus under root 3. So this square bracket will be in the denominator of denominator. So finally getting the 50 value cancelled from the numerator and denominator, this square bracket will be the resultant normalized load admittance. So this is the normalized load admittance. Now we shall get it to the distinct real and the imaginary portion. So here we shall be having 2 added with j times the square root of 3 value can be find out and will be added by the 2. It results into 3.732 here. So let me outline the intermediate value useful to solve the problem based on the single stub matching. So this is the normalized load admittance. Now we are successful to determine. So by the next step, we have to mark these values onto the Smith chart. So this is our Smith chart. We have the value of the load admittance. So the real part is equal to 2. So when we see the constant R circles here, this is the unity circle having R is equal to 1.0. Here we have R is equal to 0.0, R is equal to 2.0. So as we need R is equal to 2.0, so we are going towards the 0 values here. We need to go for R is equal to 2.0, this particular line here. Next to that, we have the imaginary part to be 3.732. So this is the positive part. So therefore in the Smith chart, we need to find the value onto the upper half of the Smith chart here. Whereas onto the horizontal line, we should be finding the constant resistance circle of 2 here. So now in this Smith chart, this will be the one circle with the constant resistance R is equal to 2. Now we need to find for X is equal to 3.732. So if you start at here, we have the 0 values and it will be having. So now if you see here, the X is equal to 0 value starts here. We have X is equal to 0.1, 0.2, 0.3. So this way we go up to 1.0, 1.2. Then we go for 2.0, 3.0. Here it is 4.0. We want the X value to be 3.732. So we have 4 markings in between 3.0 and 4.0. So this is 3.2, this is 3.4, this is 3.6, this is 3.8. So 3.732 will be in between the third and the fourth marking here. So here it should be the line. So this line should intersect with the constant resistance circle having the 2.0 value here. So this is the circle coming, and from this side this is the another constant reactance circle coming. So this is the point of intersection we can say. So let us mark this point of intersection, and now we can join it with the center of the Smith chart here. So here we have marked the point. The center of the Smith chart is here. So now we can connect the 2 points so that it intersects the scale onto the outer region of the Smith chart here. So when we join the 2 points, we come to see here, this is the marking onto the scale here. So now at this particular point where we have added the normalized admittance, we can mention this is nothing but Y suffix L here. Now in the next step, here we should be taking the distance from the center of the Smith chart up to the y suffix l, the normalized admittance point, to be the radius, and we shall be drawing a circle so that this circle will be intersecting the unity circle here. So here we take the center of the Smith chart, and this is the distance for the normalized load admittance, and we have this particular arc with respect to this particular position, and we can get it directly also. So this is the unity circle here we have, and the unity circle will be intersected at such a point here. So this is on the lower half side, and we can continue on to the upper half side also. When we see the intersection onto the lower half side, so here it is r is equal to one circle that is coming onto the lower half side like this. This is the intersection point here. So in this step, we have taken the radius centered at 1.0 up to the load admittance into the normalized that we have marked earlier by YL, and we have got this circle to intersect the unity resistance circle. So the unity resistance circle is having the one intersection on positive side and one intersection onto the negative side here. So here we can say this point is nothing but we have y suffix d here. So to see this particular intersection point, the constant resistance circle is at r is equal to 1, whereas the constant reactance circle, if you see, that is starting at this particular point and going towards this, we have here 2.0, we have here 3.0, the four intermediate markings here, we have 2.2, 2.4, 2.6, 2.8 and then 3.0. So here this is the constant reactance line at 2.6 here. Therefore, we shall be further expressing y suffix d in the small case. So here we have opted y suffix d in the small case. So this is equal to 1 minus 2.6 times j, we can see here. So this was the step number 2. In the step number 2, we have drawn SWR circle, and this SWR circle has intersected with the circle of unity resistance value, and it has finally resulted into y suffix d. So this is the value I outlined to be the intermediate value and will be helpful in further computations here. So as this is the point we have marked y suffix d, this is the point we can say this is nothing but y suffix d dash here. So this is y suffix d dash onto the another side. Now we shall be joining these points with respect to the center of the Smith chart here. So let us have the center of the Smith chart at r is equal to 1, and this is the yd dash point. So we draw a line that will cut the scale of the Smith chart onto the outer side here. So we have this particular marking, and also yd is to be also connected to the center of Smith chart. So in this regard, we have this center and yd matched here. So this is the line that we draw. So on the Smith chart, we have the marking corresponding to the YL here. We have YD also and YD dash also. Now when we cut these by joining with respect to the center of the Smith chart, we have the scale markings correspondingly. So for YD dash, we have here the value that we can have 0.199 in terms of multiplicand with the lambda here. Whereas corresponding to that of the normalized load admittance YL, we obtained the value up to 0.217 times lambda here, as we see in between these two here. So this is 0.216, this is 218, in between the midpoint here we have 0.217. In the similar fashion, when we go for the position of the stub represented in the normalized condition y suffix d here, we get the value is 0.320 times lambda here. So this is the position in between 0.3, here we have 0.31. So these are the four intermediate line for 3.2, 0.32 here, 0.34, 0.36, 0.38, and it will be 0.310. So the corresponding value we have taken on this particular Smith chart. Now in the next step, let us say this is the step number 3, we can say. In the step number 3, we shall be implementing the condition for impedance matching here. And for the impedance matching in the generalized form, we have y suffix 11 is equal to capital Y suffix D added with capital Y suffix S. So here capital Y suffix S is the susceptance of the stub here. So I mention here susceptance of the stub, or you can say it to be the contribution from the stub in the form of susceptance to be added to that of the susceptance for the microwave main transmission line. So this will be at the node point Y11. So to get it converted into the normalized form here, we get the representation of y suffix 11 to be equal to the normalized small case y11 into capital Y0, the characteristic admittance. Here the first time on the RHS we make small y suffix d into, here we have capital Y suffix 0. The second term, that is represented as small y suffix s into, we have capital Y suffix 0s. This is with respect to the stub here. Now when we are required to form y suffix s from the above equation, we get the form of the equation as, we have y suffix 11 from the left hand side minus y suffix d from the first term of the RHS that we need to get shifted to the another side here, and this is in multiplication to, we have capital Y suffix 0 that can be taken as a common from them, and it is divided by capital Y suffix 0s. So capital Y suffix 0 is the admittance of the microwave transmission line, whereas capital Y suffix 0s is the admittance of that of the stub here. Now as per the problem statement, the characteristic impedances in the form of capital R0 and capital Z suffix 0s, we can say, are provided to us. For the microwave transmission line, R0 is equal to 50 ohm, and for the stub it is of 100 ohm. And we know that the admittances are the inverses of R0, and for the stub it is inverse of Z suffix 0s. So by substitution of the values here, the next form of the equation will be, we put small y suffix s is equal to, the value of y11 will be equal to 1 there, minus, we have just now determined the value of y suffix d here, it is equal to 1 minus j times 2.6 from the Smith chart, and now it is multiplied by the ratio of the two characteristic admittances here. So it goes 100 to the numerator and 50 to the denominator. So this is nothing but the characteristic impedance of the microwave transmission line, and it is that of the stub here. So this results into the value of y suffix s is equal to positive j times 5.20. So I outline this intermediate value here. So as we have the value positive j times 5.20, so this is completely the pure admittance. The positive, it means it will be on the upper side of the Smith chart there. So let us find out the marking of 5.20. So when we have the value 5 here, so the constant reactance circles here, we have here, you see, this is for 1.0, 1.2, 1.4, this way 2.0, 3.0, 4.0, this is 5.0. We want 5.20. We go for 5.20. See, this is 5.0, this is 10. So in between we have the 4 intermediate lines. This should be for 6.0, this should be for 7.0, 8.0, then 9.0. We want 5.20. So here also we need to make 4 intermediate lines. So this will be at 5.20. So this marking I select and I join it to the center of the Smith chart at r is equal to 1. So in this regard, I have drawn a line onto the Smith chart. Now onto the Smith chart, I can represent this particular line corresponding to positive j 5.2 here. In the similar fashion, we can have a marking onto the negative half of the Smith chart. So onto the negative half of the Smith chart, here we have 5.0 and 10. So this is 6.0, 7.0, 8.0, 9.0 and then 10. So here it should be the marking of 5.20. So let us join this point also to the center of the Smith chart. So when we join these two lines, we get this particular cutting onto the scales of the Smith chart onto the circumference here. So I just mentioned minus j 5.20 here. Here also I mentioned 20. So in the next step, let us say the next step is step number 4. We shall be finding the distance between the load and the stub position. So we write load position and stub position. So therefore we can be the next step having the determination of d, the difference of distance here will be given by, we write stub position minus the load position. Getting back to the Smith chart here. In the Smith chart, the stub position is represented by the marking of y suffix d. Here we have the value 0.320 times lambda here, whereas the marking corresponding to that of the load position y suffix l, here we have 0.217 times lambda. So from 0.217 times lambda to that of 0.320, here we have to find out the difference here. So onto this Smith chart, we take this particular center, and from this center we go from 0.320 up to 0.217 here. So this is the difference represented onto the Smith chart here, and that difference we have computed. So here we have been substituting 0.320 minus 0.217, lambda is kept outside here. So the difference we obtain 0.103 times lambda. So this is the difference we have denoted by small d, and this can be outlined here for the step number 4. So getting back to the Smith chart here, onto the Smith chart we have shown this much of length here, and here we designate by small d here. Now in the previous step we have calculated the susceptance value here. So let us make it used into the next step. So from the previous step, the value of the susceptance at the stub is found to be positive j times 5.20. So onto the Smith chart we have marked the positive j 5.20 as well as negative j 5.20 before. Now let us have this particular entry used to make the determination of the required distance here. So the required distance, we shall be using this particular positive value. So getting back to the Smith chart here. So on to the Smith chart, here we have this to be 0.25 into lambda, the value here we have, and the one complete cycle if you go from the direction of towards the generator, here it will be 0.50, or from the wavelength towards the load, the direction if you take, here you will be at 0.25 and again completing this particular one cycle to 0.50 here. So from starting this particular position, we need to go in this particular direction and come to the position where we have marked positive j times 5.20. So when we take the difference with that of the 0.25 and that of this particular marking that we can see on this particular scale corresponding to the wavelength relative here, we shall show you. So therefore we get the length calculated as L is equal to, we take the value in total for the complete cycle 0.50 minus we put the difference from 0.25 to the marking of positive j times 5.20. That difference we have obtained to be 0.031. So this is in terms of lambdas, so we keep the lambda outside. So therefore we obtain the length represented as 0.469 times lambda. So here I outline this intermediate value. So when the line will be matched to the junction with the value of length 0.469 lambda, there it will not be any sort of reflection, and we can say that the perfect matching corresponding to the load impedance and that of the characteristic impedance will be obtained by this method here. So let us get back to the Smith chart where we can show you the entry of L is equal to 0.469 times lambda here. So we get the center here. From the center we take this much of distance and we measure the length L in this particular direction, that it is wavelength towards the generator until the point marking of J 5.20 comes here. So in this diagram, this is the marking here, that is for J 5.20, and here it is the marking we have shown for this 0.25 initially, but as we have a line starting from here, it will be for 0.50, and this is the difference. So this is the difference that you can show on the Smith chart, that it is 0.031 lambda. Similarly, when we have the intersection of this cutting corresponding to the negative of J times 5.20, the difference we can mark 0.031 times lambda onto the Smith chart. Here we denote this length mark surrounding to the Smith chart by small l here. Now let us discuss when this stub that we have under consideration into the next step 6 is of inductive type. So that time we can be using YD dash that we have marked onto the Smith chart here, the intersection onto the positive half. So that time it will be holding the value 1 plus j times 2.6. So when YD dash is to be utilized here, so that time the susceptance of the stub contribution can be denoted as Y suffix S dash here. So this will be resulted with the value minus of j times 5.2 that we have already marked onto the Smith chart here. So when continuing in the next step, we shall be obtaining the position of the stub, and it will be denoted by D dash. So the D dash will be computed as 0.50 times lambda. the complete wavelength range onto the Smith chart, minus here we will be having 0.217 times lambda, minus 0.199 times lambda. So this will result into 0.482 times lambda. And in this particular situation, the length of the short circuited stub will be represented by L dash, and it will be equal to 0.031 times lambda there. So here we get back to the problem statement. In the problem statement, we were provided the characteristic impedance of the line, the load impedance of the line, the characteristic impedance of the stub here. So both were of lossless type, and with the help of single stub matching, we have found the position of the stub here and also the length here. So we get back to the Smith chart here. So in this particular Smith chart, the position of the stub is shown with y suffix d, and it has been adjusted so that the length of the stub will be at 0.469 times lambda, that has been shown in this particular direction, that is wavelength towards the generator here. So this completes our problem with respect to the single stub matching with the help of the Smith chart here. In the next lecture, we shall be addressing the second topic of stub matching, that it is double stub matching, and in the subsequent lecture we shall be taking one more problem to see how the Smith chart will be helpful while the matching by the double stub type we shall be doing for the lossless type or the no reflection condition obtained by having a perfect match between the characteristic impedance and the load impedance to make the transmission line flattened here. So I hope you get the details very clear for the transmission line of microwave in the subject microwave engineering. For more details, you can subscribe to Ekeeda channel. Thank you.